You'll be fine with that too.
All right, guys, in the front, go ahead and get your ISO book and open it to your page. So where we are is we're still at 2.2 with our reading assignment, right, guys? So the first thing that I want to do is I want to kind of go over some facts. On your one pager, I want to make sure you've got the information that you need, okay? Here was the first equation. Do you have that first equation written down? Change in time is time final, subtract initial time. So if I was looking at change in time, and let's say I started and I did something for 10 minutes. What is my initial time? 0, right? My initial time.
Oh.
If I said, all right, right now I'm going to start doing exercising for 10 minutes. Okay? So if I wanted to find out what the change in time would be, you're going to take 10 minus 0, right? Which would be 10 minutes. So in your book, make sure you have this formula and you've written down what it stands for. The next thing is it talked about scalar and vectors, right? In your notes, did you say that scalar has no direction and a vector has displacement? Is an example of a vector quantity. So you have two different types of quantity. You have vector and you also have scalar. All right, you have those written down. The next thing that I want to make sure that you look at is we had on the last page of our reading assignment was talking about origin, and we were talking about adding origin and subtracting origin. Okay? So if we have two vectors that are going in the same direction, we're going to add those vectors together to get the total amount that we have got. If we have a vector that is going in one direction and then going in the opposite direction, we're going to subtract them. So let me give you an example. Remember yesterday where I had to start, right? And I put start. In this textbook, it says origin. Okay? So if I had somebody with an origin that started right here, okay? They walked 10 meters in that direction. Okay? And they stopped. And then they actually walked another 5 meters. It's asking me how much was it, right? How far did they go? This is the addition, right? So in the book, it had that. And then it had that, right? And they wrote it down as resultant. The resultant is the complete total number of the length of the arrow. Do you understand? Mm-hmm. The next thing, it was telling you, all right, say the person's here. This is the origin. And they walked 10 meters that way, but they turned back around and they walked 5 meters that way. Okay? Now, my resultant wouldn't be the whole thing, would it? What it's going to be, it's going to be the difference, isn't it? So if I look, 10 is going that way, 5 is going that way. What do you think my resultant is? 5 in which direction? 10 that way, 5 that way. My resultant going to be 5 that way. 10 going that way. So here we go. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? Complete line, isn't it? If I go back 1, 2, 3, 4, and 5, right? I still got 5 more, don't I? And that's why it's going in that direction. Does everybody understand? So if they're going in the same direction, you're adding them together. If they go in different directions, you subtract them, and whichever one has the longer vector, the answer is going to be that direction. Everybody good so far? All right, let's go ahead and go to our book. And what I would like you to do is I want you to go to page 40, please. So is everybody on page 40? Okay. So what we're going to do is we're going to do these questions and problems. Does everybody have this written down so I can erase it? How you doing, Kristen? I'm going to leave it there for a minute. So we're on page 40, and it says, identify a coordinate system you could use to describe the motion of a girl swimming across a rectangular swimming pool. So what do you think we've got? How are we going to draw this? If it is a rectangular swimming pool, and this girl is swimming this way, or do we know? Does it tell us? Okay. For a rectangle, how do we find area? Length time width time height, right? We would need to know that. So the answer for that question is that. Draw your swimming pool and to find your area, that's what we're trying to find, it would be your length time width time height. So write that in your textbook, in your ISM book, sorry. So the position along the pool length, and then what we're going to do is find our origin. Our origin would either be here, right, guys? Or right here, right? She's either going to be swimming this direction or she's going to be swimming direct direction, right? So draw that in your ISM book for question number 1 on page 40. Is everybody good so far? How many post-lets do you have? All right, so let's look at question number 2. Question number 2 says this, or number 8, 7, excuse me. Displacement. The motion diagram of a car traveling on the interstate is shown below. The starting ending point is indicated. Make a copy of the diagram. Draw a vector representing the car's displacement from the starting line to the end of the third time interval. Okay? So on your paper, I want you to draw what it says here. So on here, it says start, right, guys? Which is completely the origin. We have our end, right, guys? And then we have some dots that go in between. Everybody good so far? So it asks us to make a copy of the diagram, draw a vector representing the car displacement from the starting line to the third time interval. So here is what we have to draw. Okay? We do from the start to here. Now, I'm going to go through let me do it right. This is the start. Okay? I'm going to put my dots back down here. It'll be easier. And then I'm going to draw my vectors. Now, if you look, the only thing that I'm doing is doing what? I'm just drawing vectors. I'm showing the direction. How do I know the direction? Because I have a start and I have an end. Questions about number 2? Okay, question number 8 says, 2 students add a vector for moving object positions for t equals 2 seconds to a motion diagram. Whether they compare their diagrams, they found that the vectors did not point in the same direction and explain. So it says 2 students use a vector for moving objects from position to times 2. So here we are with a start, right? The only thing we're going to do here is we're going to put our time, correct? Time 1 and time 2, that's going to be in seconds. It says that when they compared their graphs, they found that the vectors did not point in the same direction. Now, you can have your origin here, right? This is my origin. That's the first student. Okay? Here is the second student. So basically what it's saying is you have 2 students. One student is starting on the left-hand side. One student is on the right-hand side. They're going to pass each other, and they're going back to the same place the other person started. Okay. That makes sense. Does anybody have any questions on why you draw it this way? Because it tells us they don't start at the same place and they end somewhere different, right? Everybody understand? Okay. So let's look at number 9. The motion diagram of a boy walking to school is below. All right, you ready? So we have home here. We have school here. And it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots in between. Drew the diagram. So it tells us, make a copy of the diagram and draw the vectors representing the displacement between each pair of the dots. We're going to do the same thing we did before, right, guys? I'm going to take my dots. I'm going to move them down again where I had them. The only thing I'm going to do now is I just got to draw my vectors on the direction. So this guy is going from home to school, right? This is where he begins, or the origin, as they say in this book, and this is where he ends. And all we're doing is drawing vectors. Everybody good so far? The critical thinking says a car travels straight along the street from the grocery store to the post office. To represent this motion, use a coordinate system with its origin at the grocery store and the direction of the car moving in a positive direction. Your friend uses a coordinate system with the origin at the post office and the opposite direction of the position directed. Would the two of you agree with the car's position, displacement, distance, and time interval? So what I want to do is I want to give you a couple of minutes. Read this question. It's a lot of words, right? Read this question and see if you can draw the diagram. And then I'm going to draw the diagram on the board for you in just a minute. These two graphs, you're going to draw each. Give you a little line here and draw each. They both have straight lines, right? Draw them. Then go to the next one. So that's what you're doing, right? Yes, okay. Yes. Yes. Yes, sir. And then we're going to okay, so what it's going to do is just asking you to match that. What do you have to do to make it look like that? Got it? So what you're going to do is you're going to manipulate your little detector there to get it like it. Okay? How are y'all doing? Okay, so you follow that. So what you're going to do is you're thinking, okay, we know this is the range, right? What would make it go up that way? You can walk forward it, or you can walk back from it. You can do. See, that's what you have to do. You have to see what you do. You have to do to make it work out. How do you make it go from here? How do you do that? My storage room. Okay, so it says, car travels straight along the street from the grocery store to the post office. So, see, so we have a grocery store and we have a post office, right, guys? That's what it tells us to start with. Okay? To represent its motion, use a coordinate system with the origin at the grocery store. Okay? This is my origin. And the direction of the car is moving in a positive direction. Okay. Now, to be able to show a positive direction, we are going to go right, right? So if we go right, that is going to be a positive direction. Does everybody agree so far? If we are going to go left, that is going to be a negative direction. Everybody good so far? Okay. So it says here, okay, your friend uses a coordinate system with its origin at the post office. Okay? So now I got a friend, right? I'm going to put it underneath. This is person 1. This is person 2. Is everybody good? So for this person, their post office is their origin. Everybody good so far? Is that what you got drawn? Okay. With the origin of the post office and the opposite direction as a positive direction. Would the two of you agree on the card's position? Now, if they are going in a positive direction, do you agree with it that way? Now, if they're going from the post office to the grocery store, is that a positive direction? Is that a positive direction? Is that a positive direction? That's a positive direction. Is this one a positive direction? No.
I, through P,
Okay.
please report to the media center at
Because it's going to have to. The only way it could be.
I, through P, last thing. Thank you.
The only way that it could be in a positive direction is how? Yes, exactly. So to get to the grocery store in a positive direction, they would have to come up here, but then they would be in a negative direction. What is another way that they could go in a positive direction? Is that a positive direction? No. So do you agree or disagree? Disagree. There's no way. Unless their grocery store is in a total different place than where ours is. Do you understand the instructions that it's asking you there? Okay? So far, we've done the practice problems. We went over these important information. Now I'm going to ask you some questions. What does delta T stand for? What does that stand for? Change in time. Correct. What does delta X stand for? Change in position, change in displacement. We good? Okay. What is TI stand for? Initial time. What does XI stand for? Position initial. Okay. What does TF stand for? Final time. And here we go. XF, what does that stand for? It's going to be, when we're talking about XF, we're talking about final position. Okay? So to be able to find this, you're going to take change in T. That means the difference in time. You're going to take your what? You're going to take your final and minus your initial, right? For your change in position, you're going to take your final and minus your initial. Does that make sense? Are you crystal clear with it? Okay, let's get our 4 squares out. The ones we were doing yesterday. Okay, so yesterday what we did is we did this one page here with the car, right? And how it was telling us positive and negative direction, right? We also talked about how, and I'm going to go over this again because this should make sense to you. So here on the example on the bottom of this first page, it is showing us this. Okay, you ready? All right, so it shows us this graph, kind of sums things up, right? I'm at the very bottom of this page. So what that's telling us is this is where they start. They're going in a positive direction, right? But can you tell they're slowing down? Because the length of the vectors are smaller. What does the dots represent? They have stopped. What have they done now? Turn around. Are they going? They're going, okay, they're going faster, but then they're slowing down again, and you can say they've stopped. All right? Does that make sense to you? Yeah, right? Now, let me ask you. Let me give you some numbers, okay? We're going to say this is 0, this is 5, this is 10, and this is 15 meters. This is the distance that they've traveled. Are you ready? If I ask you how far, what was their distance that they traveled, how can I figure that out? So they started at 0, right? They went 15 meters. And then, but then we're talking just the distance traveled, not the displacement, remember? So for distance, I'm going to say 15 plus 10, correct? Do you see it? They went 15 meters, they stopped, and they turned around and let's see, 5, 10, right? So the total distance they traveled was 25 meters. Do you see where I got that at? I'm adding everything. Now, if I was talking about displacement, this is different, isn't it? So this one, instead of adding it, what are we going to do? We're going to subtract 15 meters minus 10 meters. So what is my displacement? 5 meters. Are you good so far? Is this making sense? Is it understanding about positive and negative? Everybody good? All right, so let's look at our paper on our second page. So we're on second page here. So on the second page, it says, consider the motion map below. And it says time equals 0. Cyclist A and cyclist B starting to move at the right at a constant velocity at the same position on the right of origin. Okay, are you ready? So I'm going to draw it on here so you can see it, especially those of you that are at home. You're probably going to have problems because I had to take a picture of it. So what we have is we have this, okay? This is telling our positions going in a positive direction, right? So we have B here, and we have A here. Okay? B now looking at this, you kind of really don't understand what's going on until you put position down, because that's what X stands for, right? Position. I'm going to say this is at 0. I'm going to say this is at 5. Excuse me. I'm going to say this is at 10. And I'm going to say this is at 30 meters. So let's look what's going on. This is a track. 2 people that are at a race at a running track, and they are starting at 2 positions. Do you agree? One is starting at the 0 line, and one is starting at the 5 line. Does that make sense? They're running, but what happens? What happens this person is running really, really slow, aren't they? This person is running really fast and passes them and wins the race. So when this is a snapshot of them starting and then ending. Is everybody good so far? Does that make sense to you what's going on here? Two different places they start, but B finished first. We have only the position, we don't have the time. But if we had the time, we could actually find out more things, couldn't we? Everybody good so far? Okay. So now let's look at the next thing that's on our sheet. The next thing on our sheet is showing us a graph. Are you ready? So we have an A, and we're having a B. We have 3 is our time. Now, I'm right here, baby. I'm right there. So what's going on here? When you look at this, what's that telling you? Are they starting at the same place? Okay. What happens at 3 seconds? They're at the same place, aren't they? And then what happens? They go somewhere else, don't they? So this one's a little confusing, but I want to make sure you understand what's going on. They're both stopped. They both started at a different place, but as a time goes on, in 3 seconds, they are at the same place, but then they're going somewhere else. Everybody good so far? Okay, so let's see what it says here. It says you can also represent the behavior algebraic showing this, and it's telling you x equals velocity final time divided by x. So these are 2 different ways of how to draw a motion map. One has to do with position. The other one has to do with time. Do y'all have a question so far? The question says, draw dots indicating the position of an object with equal intervals, example for seconds. So if we were doing that, you know how to do that, right? You just draw those dots equally amount of time across. Number 2 says, attach an arrow to the dots indicating direction of motion. Make the arrow's lengths half the space in between the dots and the motion map easier to read. Number 3, when an object is stopped for several minutes, draw multiple lines at the same position. And number 4, make sure your sequence of arrows have a logical flow so that the motion is clearly communicated. So basically what it's doing is giving you rules of drawing a motion map. Okay? Rule number 1, the first thing you're going to do is you're going to draw the dots. The dots represent the object, right? The next thing you're going to do is you're going to do your arrows. Remember, arrow indicates direction, right? And length represents how fast something's moving. Okay? So if I had someone that went at a constant rate, I would want to try my best to draw my arrows at equal amount of length. If I wanted to say somebody started off really fast, and then they slowed down to nothing, that would show that, right? If I wanted to say they started off slow and they went faster, that's the way it goes. So the main thing that I want to make sure you understand with the motion map, you have to have the dots that shows you the model that you're using, the arrows in direction, and the length tells you the speed. Let's go ahead and flip down to the bottom. So go ahead and open yours up all the way so you can look at the bottom. Or you can do it hot dog style like this. Okay? So we're going to try to do worksheet 1. Are you ready? Yep, we got it. did about another couple minutes. Okay. So when you go back to the lab today, you're going to create maps, okay? Just like this one. So let's look to see how to use it, and then we're going to let you go. So if we have it, we have 0, 1, 2, 3, and 4. We have 1, 2, 3, 4, 5, 6, 7, and 8. All right? We have time in seconds, and we have position. Is everybody good so far? So based on this, this is a position versus time. Do you see it? Remember how we did with graphs before? So on here, what has happened is it starts at 0, it goes up to 2, goes across, and then it goes down. Right, guys? That's what our graph says. Over here, we have 0, 1, 2, 3, 4, 5, and a plus sign. Okay, these are in meters, right? Okay. So if I'm looking at this, what is happening? From 0 to 2. Do you agree? From 0 to 2, I'm drawing a vector because they're moving at a constant speed, aren't they? Moving really fast, aren't they? What happens from 2 to 4? What happens from 2 to 4? 2 to 4, they're at rest, right? Okay. And what happens if we're looking, they're at rest, so we're going to do this, right? Sorry. And what happens from after we get finished with 3 on down? What's going on? They go back this direction, right? So your graph over here is going to be started here. They're going in this direction. They're stopping, right, guys? And then they're going back in that direction. Do you understand? They're going positive, right? Stopping and negative. So the thing says, describe the motion of the objects in words. So what's going on? The object's moving forward, right? Object moving forward. They stop and they turn around. Does that make sense? Is everybody good so far? Okay, so let's look at the next one. The next one is giving us a motion map, and we have to do a position time graph. What do you think we're going to do with this one? So I'm going to keep this up here because this is my position time graph. I'm going to go ahead and draw me another one of these so I can see what is going on. So if I look, we're going to begin here. And that's at 5 meters, right? And then we're going to go this way. And then we're going to stop. Then we're going to go this way. We're going to stop. And then we're going to go this way. And then we're going to stop. All right? Now, how am I going to draw this? Start at 5, and what am I going to do? We're going to start at 5, right? And that's 5 meters, right? Okay. What time is that? 0, right? So where are we going? We're going to go down to win. The 2. What are we going to do there? We're going to do what else? We're going to go across, right? Then what are we going to do? Go down how many? To 0, right? And then what are we going to do? Oh, and then we're going to go back up. Yep. To where? To 5 again. So that's what your graph should look like. So what is going on here? They're starting at 5 meters, right? They're walking back. They stop. They continue to walk back wherever they're going. And we're going to say they're going back to my class, okay? They stop. And we're going to say they're going to stop at Miss Gore's class. And they realize, whoops, I'm not in Miss Gore's class, I'm in Miss Sloan's class. So then they come to my class. People in the back, if you please wipe down your desk and come sit down. Does that make sense to you? Okay, so what you're going to do now is you're going to take your stuff, and what you're going to need is that handout for the lab, right, guys? And you'll need your computer. That's all you need. Go on back to the lab, please. You can leave everything else on your desk.
So Marty wanted me to ask people, you think you can give me the work and you give me some, please?
Yes. Yes.
Miss Sloan, I got a question. Hey, Miss Sloan.